And I'm going to turn it over to G. Take it away. G, we cannot hear you.
Can you hear me now?
Yes.
Okay. Thank you, everybody, and thank you, Felipe, for that introduction. Thank you, everybody, for joining us in our 10th workshop GRC series on quantitative analysis. What I'm going to do in this workshop is just briefly go through some background on quantitative analysis, go through a quick example that I've used in the past, and then finish off the session with a example using the program Stata. So let's begin with defining what quantitative analysis is. Well, I think quantitative analysis is basically a collection of methods or techniques for understanding patterns of behavior. And we try to understand these patterns of behavior using numerical data, and we input them into mathematical models. So the basis of quantitative analysis is mathematical models. As opposed to qualitative analysis, where you may read a collection of texts, here we insert the data into a mathematical model, and our output will also be numerical as well. Some characteristics of quantitative analysis is because it's a mathematical model and it's based in numbers, it tends to be highly objective. And what I mean by highly objective is that it is or it is not is the result that we get. Again, it tends to focus on numerical measurement, that is how big or how long or how much. And it's concerned with consistency of the results and not necessarily the interpretability. So it's up to the researcher to interpret the results and judge whether these results make sense. Now I have here in the parentheses and efficiency. Well, efficiency in statistics means basically accuracy, or how much error is minimized in the model. So you have a bunch of data, and you have a certain degree of uncertainty that's tied to your results. So efficiency is just another word for accuracy, or the lack of error. And lastly, one of the characteristics of quantitative analysis is that it requires numerical expressions of the qualitative question or idea being tested. So that ties back to a mathematical modeling. Some methods and uses of quantitative analysis is that it's examining data for central tendency. Now the way that we do that is we look at means and variances and also a median. So a 50 percentile, this is actually supposed to say quartile, 50 percentile is the median, as some of you might know. We also can look at correlations, which is basically the degree of association between two variables. So it's whether the two variables move together, like if they move in the same direction. Histograms will give you a graphical representation of the variable. It'll show you the dispersion and how the variable is distributed. For instance, when you're looking at the histogram for age, you might see a high degree of clustering around maybe ages 45 to 55, and then it would taper off towards the 80s and 90s. Another way of graphically representing the data is to look at scatter plots or connected lines or time plots. A good example of a time plot in economics is GDP and how it changes across time. Another method in quantitative analysis that you can use is to examine differences between two or more groups. So typically what we do is we look at the difference in mean values of these two groups. So one way to do that is to use what's called a student t-test. A Mann-Whitney U-test will help you look at the difference between two groups, except we're looking at the difference in median values where the assumptions of a student t-test does not hold. A chi-square test is a method that you can use to test proportions, such as the percentage of population that has used quantitative analysis, for instance. ANOVA, ANCOVA, MANOVA, and MANCOVA is a more sophisticated technique for looking at differences. And ANOVA will allow you to look at the differences between two groups, while an ANCOVA will allow you to look at the difference between two groups and explain what's causing those differences as well. The M in MANOVA and MANCOVA stands for multivariate. So ANOVA stands for analysis of variance, while MANOVA and MANCOVA stands for multivariate analysis of variance or multivariate analysis of covariance. So for MANOVA, you're looking at more than two groups and you're looking at more than two variables. With MANCOVA, you're looking at a MANOVA, except you're also trying to explain the differences. Another method in quantitative analysis involves exploring relationships. So sometimes you may have a theory to help you model the statistical phenomena or whatever phenomenon you're looking at. And cluster analysis can be useful when you're not sure about those relationships. And then in a cluster analysis, you use statistics to try to form groups using a set of attributes or variables. Another method is principal component analysis, factor analysis, canonical correlations, and what's called a finite mixture model. And a finite mixture model is slightly different from the cluster analysis, principal component analysis, and factor analysis in that here we're actually using a regression model to group these potential classes. And one of the things in quantitative analysis we do is we test a priori relationships. So as I mentioned before, a regression analysis is a method in quantitative analysis, and there are two main techniques in regression analysis. The first one is the method of least squares, where the objective of this technique is to minimize the sum of squared residuals or the errors. In maximum likelihood estimation, what we do here is to maximize the likelihood function, or the log likelihood function, I should say. Both of these techniques will lead to the same result, except that the maximum likelihood estimation technique is not so restricted as in the method of least squares. The method of least squares, the model will be linear in the parameters. Go a little further, and it can be linear or nonlinear in the parameters. Another thing we should be aware of is the types of data that we may be faced with. So one type of data is nominal data, that we call, which stands for variables that are like gender, occupation, or race. These variables tend to not have a particular ordering. So there is no lowest or highest. It's basically a category. Dichotomous data usually refers to yes and no responses, but it can be any type of variable that is restricted to two values, 1 or 0 usually. So it's binary in nature. Ordinal data is similar to nominal data, except that there is a ordering, such as income, education, and the level of satisfaction. Integer or count data are typically data that are usually low in value, between 1 and maybe 10 or 20, and they tend to be integers. So instead of having 1, 1.5, 2, 2.5, these are all integers. It's just 1, 2, 3, 4, 5, all the way to 10, or other finite numbers. The types of studies you would see this data on, or topics, is visitation to park, class absences, numbers of natural disasters, and accidents. So they tend to be small in frequency. And finally, continuous data are data that just, that can be mapped onto the real line. So basically, you can have age, where if it was measured in, even if it was measured in years, you could have like 2.5 to stand for 1 year and 6 months. Height and weight as well is another example. Now, in addition to the types of data, we also have types of data sets. So one of the data sets that we have in quantitative analysis is cross-sectional data. So in cross-sectional data, especially with survey data, we're talking about many individuals in one time period. So for instance, the US Census will conduct a cross-sectional survey every 5 to 10 years, and you're looking at basically a snapshot of the population within that given year. Time series data may be looking at one individual across many time periods, and it doesn't have to be an individual, it could be anything, really. So here, GDP is an example, maybe changes in the composition of, or the age composition of the population, maybe consumption habits, the demand for a particular good, maybe the number of illnesses across time. Now, a mixture of the cross-sectional and time series data is a panel data. So in panel data, we have many individuals across many time periods, and typically we are following the same individual across many time periods in this case. So here I'm going to go through the process of quantitative analysis in general terms. So the process of quantitative analysis is basically first you formulate a specific question that you want answered. It's not that different from when you start any research project. So in this case, I'm looking at, are there monetary benefits from advanced degrees? So what we want to do is we want to identify the variables that we need to conduct the investigation. So we may look at the wage rate or the wage of individuals, their education levels, and perhaps some experience and other things that might explain wage. Once we have those variables, we formulate some sort of mathematical relationship between those variables. So we formulated the relationship of education, experience, and maybe a couple of other factors such as gender and whatnot to explain wage. So wage is a function of these what we call independent variables. And what we mean by independent is that they're independent, or at least seemingly independent from each other. So we formulate some testable hypothesis. So here I set the null hypothesis as the wage and education share some positive relationship, that benefits are greater than 0. Now, I want to point out that here my null hypothesis is not a statistical hypothesis. So those of you who are familiar with ANOVA analysis might say, well, how come the null hypothesis is that there is no relationship? Well, I could formulate that hypothesis, but it's not really going to help me get to the answer. So in this case, I'm going to use regression analysis to test both the hypothesis that the wage and education do not share a relationship, but in fact share a positive relationship. And here, the alternative hypothesis is simply the null is not true. One of the things that we should we should be aware of is that sometimes different types of techniques may lead to contradictory results, and that's not, even though that's not always a bad thing, because there may be some reasons why that is so, but usually all the techniques and methods should tell the same general story. So here I have, I took some data from the October current population survey. I've averaged the data from 2005 to 2007. So here I have hourly wage by education. So basically we have the average wage of no high school degree holders all the way up to doctorate degree holders, and we can clearly see that it's increasing across the different education levels. This part right here, I'm just noting that this sample includes individuals that weren't employed, so that's just kind of a note. Now, I mentioned that graphs, we can visualize relationships using graphs. So here I have graph hourly wages and experience. So here we can see that hourly wages have a nonlinear, a quadratic relationship with experience. So we can see that at about age 32 or 33 is when we hit the peak of where experience actually starts to increase the hourly wage, and then from that point on, it actually contributes negatively. And here are the results of a regression analysis with wage as the dependent variable. And I modeled the experience that we saw previously with the variable experience and experience squared. So there's a quadratic relationship. I also included different levels of education. Now, because education is an ordinal variable, we need a baseline to compare these results with. So the baseline case here is individuals with no high school diploma. So the way we interpret these results is that experience has a positive relationship with wage, or a positive correlation, but then there comes a point where the benefits from experience start to decrease. So basically, experience has an increasing, yet at a diminishing, it is increasing at a decreasing rate. So again, the effects of experience is increasing, but at a decreasing rate is what that negative sign is implying. Now here, for this first coefficient estimate, high school diploma holders make $3.77 more than those who do not have a high school diploma. Now, when we go back to this summary statistics, so that's not that far off. So we see that high school diploma holders make $15.23, and those that don't have a high school diploma make $11.18, and the difference between the two is about $3, a little more than $3. So the results are basically telling the same thing. Now we jump all the way to master's and doctoral holders. So we see that, right here, we see that master's degree holders make about, on average, $19.91 more than those who don't hold a high school diploma, and those with a doctorate degree makes about $28.25 more than those who don't have a high school degree. What I'm talking about here, I have this little, I've circled the t-statistics. I'm just pointing out that all of these coefficients were significant at the 1% level. Now, going back to the discussion on null hypothesis and how to set it and whatnot. So in regression analysis, the null hypothesis that's being tested for these coefficients is that the coefficient equals 0. So here we reject, for instance here, this experience variable. We are rejecting the null hypothesis that this coefficient actually equals 0. And it rejects it at the 1% level, and possibly less, actually. And this is true across all the other coefficients. Now, I could have run a one-tail t-test. See, what this testing the coefficient equaling 0 is a two-tailed t-test. I could have conducted a one-tailed t-test, and that would have passed or been favored over the null hypothesis that there is no effect. So I could have tested it, explicitly tested whether the null hypothesis is equal to 0 or against the alternative hypothesis that the coefficient is actually positive. So here, notice that all of these coefficients are positive. So if I would have conducted a one-tailed t-test, it would have suggested that it would have rejected the null hypothesis that there is no effect in favor of the alternative hypothesis that higher levels of education have a positive effect, or there is a positive benefit to wage from higher levels of education. Any questions up to this point? I know I've sort of given you a lot of information in a short period of time, but I'm hoping this will be familiar to those who are experienced with regression analysis. And for those of you who are interested in taking a class on quantitative analysis or statistics, that this will be kind of, this will expose you to what you'll be facing in your classes. So just to summarize again what happened, based on the results, $19.90 for a master's degree, $28.25 for doctoral degree holders, and $30 and about 50 cents for professional degree holders. And professional degree holders are those, lawyers. We may include medical professionals like medical doctors and maybe dentists as well. Now we should be careful about taking this interpretation seriously because we ignored certain factors such as occupation and, excuse the cover up here, but after this "and" it should say gender. The literature in labor economics says that gender is definitely an important factor in trying to describe wages, and so is occupation. And it turns out that occupation and gender are correlated with each other as well, because in the United States, many of the occupation that leads to lower wages are held by women. But some of the more recent research shows that, but even if you account for occupation, that women tend to make a lower wage overall. So we kind of failed to include that in our regression, so we have to kind of consider the possibility that our results are biased. Here's some tips on quantitative analysis that you want to consider. When you're transforming variables in your data, you should be aware of the mathematical consequences. For instance, taking the logarithm of a variable that includes 0 values or negative values is going to lead the software or whatever package you're using to give you a missing value or some sort of prompt that says that the value does not exist. Dividing by 0 values will also lead to some sort of missing value or errors, and taking the square root of negative values certainly can as well. And where possible, you may want to try rescaling these values. Always make sure that you have some sort of qualitative basis or theoretical basis for your models or results, because, I mean, the the models are going to only spit out what you put into it. So if your assumptions are just garbage, then you're going to get garbage back. So garbage in and garbage out. So you want to have some sort of explanation for why you get the results that you do. So for the remaining time, I'm going to go over an example using the program Stata. So let me switch over my desktop over to Stata. So can everybody see the Stata window? I'll take that as a yes. Okay, great. Thank you, Carlos. Okay, so when you open up Stata, you're going to get a screen like this. So what you do is you go to Windows, and you go to the Do Editor, and you open up a new Do Editor file that looks something like this. One of the first commands you want to enter here is Stata free. Well, Stata is not free, but it is available for those of you who want to work with Stata at the Economics Building Computer Pod. The Economics Building is located close to North Campus, but it is in Central Campus. It's near the Social Science Building. If you want to get a student version, I believe it costs $45 to get a student version. Okay, so the first thing I want to do here is to clear all the previous data in Stata memory. So you want to type clear, and then another thing you can do is you can set the memory, because sometimes you might have an extremely large data set. So in this case, I'm just going to set it to 100 megabytes. And then what I'm going to do is I'm going to use a command called insheet. And this command is specific for CSV files. By the way, the files that you can download that Felipe has made available includes a do file printout and a PDF printout of the PowerPoint slides that I just showed you, along with the outputs that I'm going to show you. So go ahead and download that file for your reference. Okay, so before I insheet the CSV file, what I want to do is I want to figure out where it is. So in this case, I'm going to use shipping accident file. So, just to make sure I have the directory right, what I do is I click on, I right-click on the shipping accident file, and then click on Properties, and then it'll give me the location of that file. So, along with the name of the file. So here I'm going to copy and paste the directory, and I'm going to put it in quotation marks just to deal with like these spacings right here. So it's always safe to put your directory and in the name of the file in the quotation marks. And then I also need to put the name of the file and then identify it as a CSV file. Okay, now once I've done that, I will click on this Execute Do button, and you can see that it has successfully insheeted or imported the CSV file. It's 14 variables, 40 observations, and we can view what this CSV file looks like by clicking on this Data Editor button that I just showed you. And this is what the data looks like. I can also check to make sure that this file that I downloaded is indeed the file that you would see in the Excel file. So let me drag that over. So this is the Excel CSV file. So what you do, the way you get a file like this is basically you just open up Excel and you include on the first row of your data, you put in all the names of the data variables, and then you enter all the data that corresponds to the variable. And then what you do is you just save as, and you pick CSV, where's it? CSV, comma, delimited. And then that will give you a file that is in CSV format. Any questions up to this point? Because basically this in-sheet command that I just used will only work for CSV files, so you have to make sure that it is a CSV file. But there are other types of files that you can import, such as a .raw file. Also, other types of ASCII files. I think it will import a .xls file. It's just that I've gotten really comfortable with using a CSV file, and it's just easy. Okay, so now that we have imported our files, some of the things that we want to do is inspect our data. So the type of data that I've imported is the integer account data. So we're going to try to run a regression on shipping accidents or shipwrecks. So this data, I have some explanations of where this data comes from in the PDF file that's available for download. It's actually shipping data. There's 40 observations, 5 types of ships, and 5 vintages, and 2 service periods within the ships. So these are the types, and these are the service periods and operating, let's see, years operated. So actually, I'm sorry, these are the years constructed, 60 to 64, and these are the years operated. And the months variable is a measure of service amount in months. So what we can do is use the inspect command, and ACC stands for shipping accidents. So I can highlight just this command and tell it to execute the selection. So when we do that, we get this result right here. So basically, the inspect command will tell us, it tells us there are no negative values, there are 8 zero values, 26 positive values, and there's 40 in all, but then we're missing 6 of them. And we can verify that we're missing 6 variables by going back to our do editor. So go back here, and we can see here that we're missing a couple of values here. You can also sort the variable so that it's convenient. It's conveniently sorted so that you can locate all the missing variables. Okay. We also notice that shipping type is, some value between 1 and 5, and the type, precisely which type it is a dummy variable. So a dummy variable meaning that it's a binary variable. It takes the value between 0. It takes a value of 0 or 1, and this is true across all these other variables, as you can see. Okay. Now, just so that you know, I can also just type in the inspect command or any other command in this command line right here. So I could have typed inspect ACC, and it'll give me these results. The reason I prefer the do editor is because you can save your results. You can keep track of what you did. So I may want to write a comment here saying, missing, what was it, 6 variables, 6 observations. And the way you close the comment is put 2 more slashes here, because if you don't put the slashes there, or you just write it out like this, and you were to run the entire do file, it'll give me you see how it tries to pick up this missing 6 observation comment as part of this inspect command. So you want to put it in between these 2 slashes to comment it out. And some of you that are familiar with programming might be, might know these types of tricks. Okay, so I showed you the inspect command, and I can do it with all these other ones as well. Another command I want to show you is the gen command. Gen command is used for creating new variables. So let's suppose that I wanted to create the log of accidents. So simply what I would do is I would define a new variable that I call LACC, and then I say equal to the natural log of the variable ACC. Okay? And then we select this option, or we select this command line, and then we just execute. And it's telling me that it's missing 14 observations. Now, the reason we have 14 missing observations is, one, because we are missing some values here for the accidents data, but also we have 0 values for accidents as well. So remember that when you have 0 values and you're taking a log of it, the log of 0 does not exist. So basically, we ended up losing more data because some of these values are 0. So let me go back to the do editor. And let's create another variable called, so we had the month variable, and we saw that the month variable is, it's got a whole range of values. So let's just create a simple variable called month1, and it's just simply month plus 1. Okay, hold on a sec, something. Oops. Okay. So I made a little mistake here, right? So the variable is called months, and I typed in month. So you notice how it tells me that month is an ambiguous abbreviation. So I'll fix that. And we're missing some values here because we are most likely missing some values in the variable month. So let's see, months. And we're missing 6. So that's why we're missing 6 here when we created this new variable. Okay. Another command that's useful is the summary statistics command. Now this one is going to be used a lot by people. So the command is sum, and we just do all the variables that we want to see what the mean, the minimum, the standard deviation is. So let's just type in a couple of these. So TA, TB, let's look at T60, 64. Let's also look at the months. Select that, and we get our results. So, for the TA, TB, and T60, 64, we have, all the values. You can see that the sum command, the summary command, dropped 6 observations because they were missing. And you can't take the average. You can't include a missing value when you're taking an arithmetic average. So we have an average of 10.47 accidents, shipping accidents, average of 48.11 months. And here we have 20% of the observations that are type A, 20% that are type B, and 22.5% that fall into the 1960 to 64 year constructed indicators. One last descriptive statistics command that you can use is called the histogram command. So let's look at a histogram of accidents. Now I'm going to tell Stata that this is a discrete or a count variable because accidents is actually an integer value. So it's discrete, and I'm also going to ask it to label the label the axis and also have the y-axis be a frequency instead of density. So when we do that, okay, might have done something wrong here. Oops, I misspelled discrete. Okay, so this is the histogram that we have. So these numbers right here, this is the frequency. We have 8 here in the 0, and all the way over here we have, a couple of observations that fall in the greater than 20 category. But for the most part, we can see that this distribution is really high, and then it starts to diminish real quickly, right? So it starts to fall. Now there are two types of distributions, or two primary types of distribution that's used in count data regression analysis, and they both fall within what's called a Poisson family. So the first one is a Poisson distribution. Now, one of the characteristics of a Poisson distribution is that the mean of the Poisson distributed variable is equal to the variance. The other count data distribution that I'll go over is called a negative binomial distribution. And a negative binomial distribution is basically a combination of the Poisson distribution and a gamma distribution. And what it's used for is to model count data that is Poisson, except that there tends to be what's called over dispersion of the variance. So basically here, if this variable accidents was truly Poisson, we would tend to see something a little bit more symmetrical, something that is centered, around maybe the lower numbers, and we wouldn't have this kind of, these really high values towards the right tail. But just to show you the difference in fitting a Poisson regression versus a negative binomial regression, I'm going to go ahead and model both. So the command to model a Poisson distribution is Poisson, and then the dependent variable first, and then the list of independent variables. So here I'm going to include TB, type B, type C, type E. So for the types, because this is a categorical variable, we have to leave one of them as the base. So the base variable is going to be type A in this case. So I'm going to include all of the variables that indicate type except for the reference variable. The same thing goes with the year constructed variable. So in this case, I'm going to use 1960 to 64 as the base variable and use 65 and 69 and T70 and 74, and T75 and 79 as the indicator variables. And then I'm also going to include the operating variables here. So in this case, it'll be 075, 79. And then finally, I'm going to include the months of service amount months. So I'm going to highlight the Poisson regression and then tell Stata to execute it. And here are our results. So we find that the types here, type B relative to type A is actually, there's a positive effect from being, a type B, or positive correlation. With type C tends to have a lower number of accidents compared to type A. Now here, let's see, we see that all the other year constructed indicators are positive relative to the baseline year, which is 1960 to 64. Months have a positive correlation, and the year of service, the operated service operator, 75-79, has a positive correlation compared to 60 and 74. Now, one of the cool things about Stata is that it will detect mistakes in, if I were to include the type A variable and those other variables, it would result in what's called perfect multicollinearity. Now, Stata has a command line that actually detects perfect multicollinearity, and just to demonstrate that it does indeed do it, I'm going to include here type A and the T60, 64 variable, and that other the operating indicator. So that was 6074. And watch. So notice here that it just, okay, so it did drop the one that I wanted, but it did drop one of the type indicators. Actually, it did drop the type indicator this time. Oh, I'm sorry. That's because I forgot one of them. Okay, I forgot type D, didn't I? Type D. So let's see which one it drops. Okay, so see, it dropped type E automatically, and it also dropped this, the service, or the constructed indicator, and then the operation indicator. So Stata will do that for you automatically. It's just that it's better for you to do it yourself because you want to control which one is the base. Any questions up to this point? Because I know I'm kind of going through this stuff pretty quickly. Okay, so in the last 5 minutes, I'm just going to show you the results of the negative binomial. So the command is mbreg, and I'm just going to copy and paste all of this. Yes?
Excuse me. Just a reminder that we still have the evaluations.
So in the last minute, I'm just going to go through negative binomial distribution. And one of the ways, this is the way to test whether a negative binomial distribution fits the count data better than the Poisson distribution is to look at, just run the negative binomial regression and then check this alpha parameter. So if it was, so Stata actually tests whether an over-dispersion exists. So alpha is actually the over-dispersion parameter, and Stata will actually test whether this over-dispersion parameter is significant. So in this case, we see that we reject the null hypothesis that the alpha parameter equals 0, which is in favor of the negative binomial regression over the Poisson distribution. So another way, that's one way to check. Another way that we can see that the negative binomial distribution or the regression is superior is to look at the log likelihood value. So this value, negative 83.30, is clearly greater than negative 87.65, which suggests that this model has, explains the data much better. Okay? Now, if you, so again, I included a printout of this output and, a printout of the do file with a whole bunch of comments on there. But if you have any further questions, feel free to see me over here at the GRC, make an appointment. I would love to go through some more techniques with Stata with you. Other than that, if there's no questions, I thank you for joining us in this workshop.
Thank you guys for joining us. Thank you, G, for an excellent presentation. So before I lose you guys, just a reminder, here are the documents that G mentioned for download. And I'm going to show you the evaluation link now. Just look for it in your browser. And if you cannot find it, I also have it here in the chat window. So please don't forget to fill in the evaluation, give us your feedback so we can improve our services on your behalf. Any more questions to G?
Thank you, everybody, and have a pleasant night.
Evaluation before you leave. I'm gonna stop the recording now.